Grand Canyon is a beautiful landmark, yet the difficulty of finding a parking spot can detract from the visitor's enjoyment. The number of Grand Canyon visitors are listed in the table for various years. So here's the table. Describe the data with the graph. Okay, so we got ourselves information, some real world information about the number of visitors. So 1960, 1.2 million visitors. 1970, 2.3 million, 1980, 2.6, and so on and so forth. So the last known value we have on this table is 2010, which is going to be 4.4. Okay, so the first thing we have to do is come up with a way of transforming the calendar years into something that's a little bit more practical. Because if we leave it the way it is, we run into some issues. How are we going to scale, how are we going to graph that? If we put years here, where do we put the year 1960? You know, are we going to count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way out to 1,960? That's pretty ugly. So, okay, scaling. Okay, let's scale it. Okay, so we're going to count by multiples of something. So we're going to do like 500, 1,000, 1,500, 2,000, 2,500. Okay, so there's scaling. We like change the multiples, 500, 1,000, 1,500. But now all our information is like right around here, right? Like right in there is like 1960, and like right around there is 2010. So our entire picture is going to be like right there. That's also pretty ugly. So those are not good solutions. So one good solution we're going to do is to transform the calendar years into the number of years from a particular starting point, a t-value. So we're going to let, I'll just put t. We're going to let t equal the number of years since, and then we're going to pick a starting point. Every word problem is going to be a little bit different, so there's nothing special about this year, but we're just going to pick 1960. It's a nice, convenient, round value. It happens to be the smallest value on this table. So we're going to pick 1960. And so now, when we graph these things, when we graph 0, this represents 1960. T is equal to 0 in 1960. When t is 1, it would represent the year 1961, 1962, right? So now we have a way of graphing it and getting something that's a little nicer. So we're going to translate each of those years into a t-value, and we'll get a table that looks like this. Right? 0, 10, 20, 30, 40, 50, and so on and so forth. So say 30, t equals to 30 represents what year? 1990, right? 30 years after. You can think of the t-value as sort of, think of it as like sort of a born-on date. Someone was born in 1960. How old would they be in 1970? 10 years old. That's what the t-value is. So we come up with t-values, and that'll allow us to come up with a graph that looks a little nicer. So we do that. In this class, we almost never use calendar years when we're working with the math and the graphing. We got to convert it to a t-value, graph it, come up with equations, and then afterwards we come back and transform it back into a calendar year when we want to describe our solutions. Good? Good, good, good? Okay, so if we look at our results then, we see that the number of visitors to the Grand Canyon has been increasing since 1960. That's probably due to ease of mobility of our country, could be one thing. So, you know, compared to 1960, more people have cars, and, you know, hopefully our interstate highways are a little more interconnected. What else?
There's more people in the world.
There's more people both in the US and the world, right? And so, in order to get there, what has improved dramatically since 1960 other than cars? Transportation-wise, what's really big now compared to 1960? Planes, right? Access to airplanes is a lot more common now, or in 2010, than it was in 1960. There were, of course, planes in 1960, but they were still pretty expensive, right? The commercial airline industry was still kind of a high-end product that really maybe the wealthier people could afford. It really wasn't very accessible to a lot of people. It's a lot more accessible. It's not accessible to everyone yet. There's a lot of people that can't afford to jump on a plane and fly somewhere. But there's more people that can afford it, right? Okay, so that might be one of the reasons. More people in the world, and transportation has been improved. So more people are going to the Grand Canyon, and so we see a rise. Okay, the first thing we want to do with our data is convert it into something that we can work with. So get rid of those calendar years, get it into a new table that has t-values instead of calendar years. And now what we want to do is we want to graph those. Those are ordered pairs we can work with. And so if we graph those, we'll get something like this, right? All those individual dots represent the ordered pairs from our tables. And then, so this is called the scattergram. When you graph a bunch of ordered pairs like this, it's called a scattergram. So we want to be able to create a scattergram, and now we want to see if there's a pattern between the dots, if they form some sort of a pattern that we can see. And hopefully you can see that they sort of look like they're in a straight line. Not a perfect line, right? Real world data is often very messy, so it's not exactly a line, but they sort of look like they could be a line. So that's what we're going to be focusing on in this chapter, plus we're in chapter 2, so we know we're working with lines, so that's another hint. So what we're going to do is we're going to draw a line to kind of guesstimate where all those points are. Now, very important distinction, we are not drawing a line that includes all the points. That's not possible. They're not in a line. We're not going to do some sort of wiggly thing that makes sure to include all the points. We don't want to do that. We want a straight line. We don't want a line that includes the most number of points either. Right? We don't want to go, well, include the most. No. We want a line that sort of goes among all of them. For instance, like let's say that these 3 points, I wanted to come up with a line that kind of comes close to all 3 points. Is this a good approximation? No. Is this a good approximation? Well, it goes through 2 of them, but it's completely ignoring the other one. Maybe something that does something like this would be better, where it doesn't really touch any of the 3 points, but it's, it kind of breaks them up. It goes kind of in the middle of the 2. You can kind of think of a tug of war between the points below the line and the points above the line. There's some sort of influence that all the points have had on the line, even though none of the points are actually on the line. Good? Okay, so we want to come up with a line that sort of kind of goes through these points, and we're just going to eyeball it at this point. So if we just eyeball it, it could be that right there, right? So at this point, we're not doing any actual math or anything. We're just going to look at it and eyeball it and draw a line. Notice that in this case, none of the points are on the blue line, and that's okay. We're not looking for a line that includes the most number of points, or even any of the points. But it does look like it's sort of in the middle, right? There's 3 points above the line, 3 points below the line, right? It just sort of looks pretty good. But it's just a guesstimation. I'm just eyeballing it, so somebody else could come up with a different answer. So there's plenty of good answers at this point. Maybe it's the blue line, maybe it's that red line, maybe it's that green line. Several good possibilities are available at this point. Okay? Good. Okay, so we're going to draw our scattergram. We're going to look at it and judge sort of where a good line can go through it. And then we're going to use that line as an approximation of the relationship between the values in the independent axes and the values in the dependent axes. So in this case, the calendar, the t-value years, and the number of visitors that go to the Grand Canyon. Okay, so we call this a model. A model is a mathematical description of an authentic situation. We say that the description models a situation. So we're modeling the number of visitors to the Grand Canyon as a function of the t-value since 1960. That's what we're doing. Now when we create a model, we can describe that model with an equation, which we will eventually. But for now, we can just describe our model with a picture. We can just draw a line. That blue line is our model, right there. There's my model. I'm describing the relationship between the t-values and the visitors, the calendar years and the visitors to the Grand Canyon. Okay? So I can use my model to approximate things now. So if we look at, for example, the year 1960 itself, or in fact, let's go to the t-value of 50. What year does that correspond to? When t is 50, we're talking about the calendar year 2010, right? So there are two values that correspond to t equals to 50. There is the blue dot value, and then there's the black dot value. The black dot value is the real answer. We know what that answer is. That answer is 4.4. So I know that there were 4.4 million visitors in 2010. That's the real answer. The blue dot is my approximation. The blue dot there is being influenced by all the other ones. That's how we created that blue line. So for the year 2010, we would stick to the real information. Since we already know that, it's 4.4. There's no need to approximate it in that year. So if they ask you what happened in 2010, there were 4.4 million visitors. You kind of ignore the approximation, right? But now what happened in 2011? Well, I don't have an answer to that, right? We don't have any real information. That's when we get to use our guess. And our guess, our best guess, is that blue line, okay? So, for instance, if I wanted to guess what's going to happen in the year 2018, I don't have that real information on there. So the first thing I'd have to do, 2018, I'd have to convert it into a t-value. What is the t-value associated with 2018? 58. Okay, so I have to go across, find 58, go up. Okay, and what does that sort of correspond to? What would be your best guess according to this model? In the year 2018, there's going to be approximately like 5.5 million visitors, right? That's not like a very precise guess because, you know, we just eyeballed this, but I'm pretty sure it's a pretty good guess. I mean, I know it's probably not going to be 1 million guests, right, visitors. It's not going to be 2 million visitors. It's not going to be 50 million visitors. It's going to be somewhere in the neighborhood about 5.5 million according to this model. Good? Questions? We can also go backwards and figure out in which year was the first year that we saw 4 million visitors to the Grand Canyon. So we go to the vertical axis, find the 4, go across, run into the blue line, come back down, and we get to approximately where? 30 something? Like 37-ish. And again, you know, if you did this yourself, you might have a slightly different answer, and that's okay. We just, you know, there's several pretty good answers. So 37, which would correspond to what year? 1997. So we would say, according to my model, right, meaning I'm guessing, my best guess is that in 1997 was the first year that the Grand Canyon saw 4 million visitors. Right? But they saw 4 million visitors in the year 1997. Any questions so far? Okay, so now let's practice creating this scattergram with our calculator. It's one of the skills we're going to have to learn to use. So hopefully you all have your calculators. So I'll assume that you guys don't have any prior knowledge of these calculators. So I'll sorry if I insult you if you already do know, and I'm going too slow for you. Okay, so first thing. Come on. Oh, that's fine. So the first thing to note is that when you turn it on, there's a little button down here. This is the on button down here. So you turn it on, and you might appear in some weird screen that you don't recognize. So in order to get out of there and go to their main screen, you're going to have to quit. So there's a little word quit right over here, right above the button that says mode. Alright, so one thing about these calculators, these are based on old school technology that doesn't have, you know, pre-touch screen and whatnot. So back in the old days when they had a button and they wanted the button to do lots of different things, this is one way they would do it. So this button says mode on it. If you hit the button, it'll do mode. For instance, let's go down here where it says 7. If you hit 7, it's going to type the number 7. But if I wanted to do one of the other things, like if I want this button to be a letter, like the letter U or the letter O that are right above it, then they put it in different colors. And then over here is the thing to set off the colors. So if I hit second first, and then I hit 7, it'll activate the blue. So it'll be that'll be that. So we'll practice that more in a second, but let's do quit first so I can get out of here. So some of you guys are in a weird screen, you need to quit. So that's this little value right in there. So you hit second and then quit. Oops, see second, quit. So that'll take you to the main screen. Now your main screen might have something on there, equations, calculations, something from before. So you're going to hit clear and it'll wipe the screen and give you a clean slate from the main menu. Okay? Everyone good so far? Quit and then clear. That's all you have to do. Second, quit, and then clear. That should take you to the main screen, and you can start from scratch here. Okay, now the first thing we need to do, since many of you are just now cracking open your calculators, is this. Go to mode. So we want to hit mode, not quit, mode, and it'll take you to this screen. And I want to make sure everything's flush to the left here. Normal, float, radians, functions, connected, sequential, real, full. If your calculator screen has even more options, I'm pretty sure everything flush to the left is going to be okay. So that way we're all working with the same calculator settings. Leave the clock set thing alone, and if there's something else below there, leave that alone. Okay? Now how do you change it? Well, you use your arrows. You got to go up, down, left, right, and then like if I wanted to put it in polar, this POL, then I would hit enter, and it would change it over to pole. But I don't want that. I want everything flush to the left. I definitely want it to be in function mode. So I'm going to go over to the left and hit enter. Okay, particularly some of you guys that got like that are borrowing calculators from the school, they sometimes come in weird settings. Degrees versus radians, functions versus pole, and all that. Okay, we're all good so far? So that one we got from hitting mode. Mode takes you to this screen. Use your arrows, up, down, left, right, select everything to the left, hit enter to select something. Good? Okay, so now let's quit out of here again. Let's go back to the main screen. So you're back to your main screen. So there's a few things we're going to learn how to do with our calculators. One of them is to create scattergrams. So to do that, the first thing we're going to do is go over here where it says stat. This button that says stat, click there. And this is another thing about old school technology before touch screens and all that. These were menus. So here are the menu options under edit. Edit, sort A, sort D. And then if you hit to the right, you get all the menu options under calc and then all the menu options under tests. So that's what we get. It just so happens we want the very first one in the very first list here. We want edit under edit. So as soon as you hit stat, you're just going to hit enter because that's the one we want. Edit. Enter. Okay, so here is a place where you can input information, lists. List 1, list 2, list 3, whatever you like. So this is where we're going to input the values that we want to create a scattergram with. Okay, so we want to first of all get rid of these ones. These are not useful. So I can hit delete to get rid of them one at a time. So the 89 disappears, that number disappears, that number. Okay, but it could be a very long list. It could be a case where there's hundreds or thousands of numbers. I don't want to go one at a time. So the other thing we could do is to go up, select the L1. Make sure it's dark the way it is right there. Select that guy, and then hit clear and enter. That erases everything underneath it. Okay, good. Questions? All right, so we want to do the same thing for L1 and L2. Now notice a very common mistake. If you want to delete an individual number, like I want to delete that one, I hit delete, and it'll get rid of the 2.6. But if I want to get rid of the entire list, if I hit delete, it's just going to delete the whole list. Now L2 is gone, right? So you don't want to delete the list. You want to delete individual numbers. To get rid of these guys down here underneath the list, you hit clear and then enter. So you make sure you highlight the L, make the L dark, and hit clear and enter, and that'll erase the ones underneath it. If you select that, make it dark, and hit delete, it's just going to delete the whole list. Delete. Now the list is gone. Okay, Okay, well, if you did do that, how do you get it back? Well, you got to hit Stat, and you got to go down where it says Setup Editor, Enter, Enter again, it'll say Done, and it'll kind of go back to the default settings, so it'll bring back the lists that you deleted. 1, 2, 3, 4, all that jazz, okay? All right, so let's make sure L1 and L2 are clear. Clear, Enter. And now let's type in the values we want to create a scattergram with. So, where are they? They are here. So these are it. Man. So we input the t values into list 1. So we want to type in 0, 10, 20, 30, 40, 50. Right? Those are the t values that we have. Yes. So type in the number, enter, type in the number, enter. And then we want to do 1.1, enter. And then 2.3, enter. 2.6, enter. 3.8, enter. 4.8, enter. 4.4, enter. There we go. Make sure that they match, right? Because these are ordered pairs. So if I made a mistake and I didn't put this one, delete that one. If I made a mistake and left it like that, it's going to be a problem because the calculator is not going to know what to do with that 50. These are ordered pairs. So we're going to ask it to graph them as ordered pairs. So it's not going to know what to do with that 50. So make sure they match. If they don't match in length, you know there's a problem. You might have messed up somewhere. So 4.4 was the last one. Okay, so we input all our values into our list. We're good to go now. Okay, now we got to go over to where it says y equals. That's our next step. See this y equals over here? Y equals. That'll take you to this screen. This screen, for now, we're not going to do much with it. So we want to make sure there's nothing in it because it might cause a problem. So if you have something written in there like an equation like 3x plus 6 or something, if there's already some equation in there, for now, we're not going to deal with it. So just hit clear. If there's others down there, hit clear, 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 delete them. Notice there's a couple hidden down here. It goes down all the way to y sub 9, y sub 0. So make sure they're all clear. And that way we don't have any problems now. We'll revisit this in the next section of what to do with this screen. Okay. All right. So next we're going to go to stat plot, which is the little blue writing above the y equals. So we're going to have to take advantage of the second button again. So second y equals will take me to stat plot. Okay. So stat plot gets me to this screen right here. And this screen gives us options of plots, and we're going to really be dealing with these 3, 1, 2, 3. So we can use our arrows to select either of them. Doesn't really matter which one you choose. So let's just go with 1, enter. And now we got a variety of things. We want it to be on for sure. So use your arrows if it's off. So see, you can go left and right to select on. Hit enter to select it. Okay. And then we're going to go down by 1, and we want to tell it which type of graph we want to do. And at this point, we're going to do a scattergram, which is a bunch of dots. That is the very first one. So I already have it selected. If you have a different one selected, like maybe yours is this one, we just use our arrows, left and right, to select the little dots, hit enter, and then choose the one we're using. Okay? Next, we're going to go down, and we're going to tell it where are the x and y coordinates. Well, I put them on list 1 and list 2. So that's why I have L1 and L2. It doesn't have to be those. If on if you put the values on list 3 and list 5, then that's fine. Put L3 and L5. Okay. Now, what if you have to change it? Well, if I want to change it, L1 is located above the button 1 in blue. L2 is above the button 2 in blue. So if I want to change this to like L1 and L3, I would hit second first to make sure that it's in blue, and then I go to 3, and that'll change it to L3. Okay? So use the ones that you've chosen. Notice that the A is for alpha, it's for green. So right now the little cursor is blinking A. So for instance, right now if I hit the button 5, it's going to type in a U because it's in green. See, it types in a U. So you just got to be careful that if you want a 5, you got to get rid of the lock. See, now it's just the little cursor is just a little black cursor, a little black box. Now the 5 will be a 5. Okay? Or if I want an L5, then I have to hit blue, second shift, 5, and now it'll do an L5. So second L5. Okay? All right, but I wanted L1 and L2, so I'm going to clear that one. Second L2, L1, L2, I'm good to go. Okay, this is just a little choice. You get to graph a little tiny little box, or a little plus symbol, or a little dot. Doesn't really matter which one you choose. Personal preference. Okay? All right, the next thing we want to do is go over to the window, and we're going to tell it the window we want to observe in our coordinate axis system. So that's just going to come from looking at our data. So the input values range from 0 to 50. So if I make the y minimum a 0 and the y maximum of 50, it'll cover the information that's in our scattergram. Okay. Scale means the little tick marks on there on the scale. How many? It counts in multiples of that. So it'll be 0, 10, 20, 30, 40, 50. Right. I'll show you what that is in 1 second. I think it'll be clear in a minute. All right. The y minimum. Well, this just goes from like 1.2 to 4.8. So I don't really need very big numbers. Let's just go from 0 to 5. Leave the scale alone like that. And now we're ready to graph. So it'll look like that. Okay. When you're done with this, so on this screen, make sure you type in all these numbers the way I have them here. And when you're done with that, hit graph. And it should look like that. So everyone should be getting this right now, right? Good? Okay, so I'm just going to play with this back and forth so that you can see what happens when you change things on the x scale and y scale. So remember that I went from x minimum 0. What if I went back and changed x minimum to negative 100? See, now this goes all the way out to negative 100, and all my little dots are over here, so it just makes it ugly. Because there's this whole space that's empty, that doesn't graph anything. Okay? So that's what happens there. I could go to the window and change y maximum to 1000. Graph. And see how ugly that is now? Because this goes all the way out to 1000, but the biggest number we had was 50. So all my information is kind of crammed into this tiny little space right in here. So that's why it looks really ugly. So we got to be careful. But that's what the x minimum and what x maximum do. So let's go back and change it back to, let's make it from negative 10 to positive, let's make it 100. Oh, by the way, another distinction, this button is subtraction. It's an operation, right? Subtraction symbol. This button over here is a negative number. You cannot interchange them, right? So if I hit right here, instead of negative 10, if I hit subtraction 10, it's going to give me an error. It doesn't know what that is. Try and graph that. Oh, that's weird. It's supposed to give me an error. Subtraction 10, graph. Oh, it automatically changes it. Now it's getting smarter. Well, before, it would give you an error because it was a subtraction symbol there. So anyway, be careful. This is a subtraction. This one's a negative, so you have to be careful about which one you choose when. So at any rate, so we have that. Now the scaling, look at the scaling. I have it at 10. So this means that right now, each of these little tick marks down here is a multiple of 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That's what that little thing means. If I go back to window and I change the scale from 10 to 25, graph, now it'll do 25, 50, 75, 100. So it's up to you to change it. It depends. Sometimes, you know, it makes sense to have a big one, a big number for scale. Sometimes it makes sense to have 1 or a half or something like that. Okay, so you can play around with that. Okay, so let's just go back to 0 and 70 for this thing. That's pretty much what we needed. And let's go back to making this 10. There we go. So here's the one I have. So depending on your choices for your X-min, X-max, and you know your values in your window, the actual picture that you have might look a little bit different. Okay. Now, if you're looking at that, it's still kind of hard to judge what these are. Like, what is that? What value is that? So to figure out what numbers these are, we're going to hit the button that says trace. Trace is going to create that little blinking cursor, and it's going to tell me where it's at. So right now it's blinking at 0, 1.2. And it's a little bit off screen, right? So that makes me think that maybe I should go back to my window and go a little bit beyond the 0 so that I can truly capture that point right there. So I'm going to go back to window, change this to -10 again, and then go back to graph. See, now this starts at -10, so I know that the 0, 1 is going to look good. So I'm going to hit trace, and there it is. So 0, 1.2 is one of the values that we have. And now if I hit the arrow, it'll go to the other ones so that I can tell which is which. I can tell they're ordered pairs. So right now it's blinking at 40, 4.8. Good? Any questions? Okay, so this is how you create a scattergram. So let's go back to our PowerPoint over here. Okay, so we were looking at the Grand Canyon information. We got calendar years and visitor information. And then we created a table. We were able to create a scattergram like this one. From that one, we judged, you know, just kind of eyeballed it and drew a line that sort of came close to all the points. And then we're going to use that. We used that as our model to be able to make some predictions. And now we're able to recreate that on our calculators so that we can work with scattergrams on our calculators. We'll do other things with our calculators and scattergrams starting in the next section. So, you know, it's a skill that we will use a lot in this class, creating scattergrams with your calculators. How about this example now? The percentage of cell phone users who send and receive text messages multiple times per day are shown in the table for various age groups. Okay, so we got age groups from 18 to 24, 76% of them text multiple times per day. 25 to 34-year-olds, 63, and so on and so forth. So obviously the younger group there, 18 to 24, has got the highest percentage of people that text multiple times per day. That still seems a little low by today's standards, right? So I don't know in which year they took this information from, but I don't know, maybe it could have been back in the early days of texting when it was still kind of a new thing. I'm sure none of you remember that, but who remembers flip phones? Remember that thing that they had with the alphanumeric system where the number, like the number 7 was letters, so you had to like spell out things with numbers? Yeah. It was not fun. Maybe that's why so many people were not text messaging multiple times per day. Who knows? I suspect today it's probably much higher, but we're just going to work with the information we have now. Okay, so real world information is messy. We saw in the previous example that we had calendar years and that presented a problem. So we converted calendar years into t-values. Here we have another issue. We have age groups, 18 to 24-year-olds. That makes things messy. Graphing that, working with that to create equations, it's messy. So instead what we do is come up with a representative age for that group. 18 to 24-year-olds, we're going to represent them with 21-year-olds. We get that by adding the 18 to 24 together, dividing by 2. It's the middle of that age group, so about 21. 25 to 34-year-olds, we add the 25 to 34, divide by 2, we get to 29.5. A 25-and-a-half-year-old is sort of representative of that age group of 25 to 34. Okay, so we use a representative age value for that group, and now we're just going to work with the representative age value. Okay, that's how we deal with these grouped data, grouped age groups. Good. Okay, so now we have a table we can work with. We got 21, 76. 29.5, comma 63, 39.5, comma 42. Okay, so we can use those values to create a table, right? Why don't we do that with our calculators real quick? So go back to your calculators. List 1, we're going to put in those values. List 2, we're going to put in the other values. So we go back to stat, edit, hit enter. And now we want to get rid of the other ones. Now, if you know you're never going to use these points again, you're done with that problem, you're never going to revisit it again, you can just hit clear, get out of there, you're fine. Or if you want to save them for later, then we got other lists over here. I can use 3 and 4, for instance. So I'm going to use 3 and 4. I'm going to input the 21, 29.5, 39.5, 49.5, and 59.5 into this list. And then L4, I'm going to put the corresponding dependent values. So 76, 63, 42, 37, and 17. Like that. Okay, so now I have new ordered pairs. So I'm going to go over to stat plot, hit enter. The reason I went in here is because I had to change these. This was still graphing L1 and L2, but I changed it. Now I want to graph L3 and L4. So use your arrows to go down to where the x coordinates are, and you're going to hit second, and then L3, and then down, and then second, and then L4. Okay? Next, when you do that, next we're going to go back to our window now. And again, I'm going to choose a window that will do a pretty good job of capturing these ordered pairs. So looking at my information, they go from like 21 years old to 59.5 years old. So I guess I could choose 20 to 60, and that would capture the values. And for percentages, they go from 17 to 76. So I could do like 15 minimum to 80. And yes, this would capture the information, so hit graph. There they are. However, it's a little misleading. Be careful, because these lines here don't necessarily represent the vertical and horizontal axi, right? Depending on what we did. So it might be more convenient to go ahead and extend it to a place where we get to see where the x and y coordinates are. So even though I don't need to, it usually makes it nice. It often makes it nice to be able to go back to say like -10. And now when I graph it, I get to see where the vertical axis is, right? And then I'm going to go back to window, and I'm going to change this to, 100. And I'm going to change the y minimum, again, just to be able to see where the axis is to like -10. All right, something like that. Good. If I wanted to have a better idea of, sort of guesstimating where this is going to end, I'm going to extend this up a little bit more, which means I'm going to make my y min a little bit bigger. So let's make the y max a little bit bigger. Let's make it like 120. See what happens there? Something like that. So now I have a better idea of where it is in relation to everything else. Good? Okay, so we got our table. We were able to transform the age groups into something useful. We got a representative age. Then we took our calculator, we created a scattergram. Now that we created a scattergram, we can eyeball, right, draw a line that can kind of approximate them all. We can say, let P be the percentage of cell phone users at age A who send or receive text messages multiple times per day. Find a linear model that describes the relationship between A and P. So we created the little scattergrams. So we used our calculator to get a better, more precise answer. But just roughly speaking, they kind of look like this, right? Something like that. So we're gonna use that to come up with an approximation to all those. And my approximation, I'm just eyeballing it, is just going to be something that looks something like that. In this direction, we have the variable A, which represents age, right? age. And then in this direction we have P, which is the percent. The percent of people in that age group that that text message multiple times per day. Okay, so you know the way I drew it here, it's hard to really make guesses because there's no scaling on here for me to do that. So if you had a nice grid, a nice graphing paper, you know, that kind of did that, then you can use it to make a good estimation about what that is. Same in this direction, you know, we have to have nice scaling to figure out what that is. So that's why our calculator is useful, since it automatically gives us a nice way to do that. So this is one such way. Right, so if we did a nice graphing paper and we graphed all the little individual dots and then we drew a line and kind of eyeballed it, here is one potential answer. So the place where the model, right, the line is our model, the place where that line crosses the vertical axis is the vertical intercept point. But in particular we're using P, so we're going to call that the P-intercept point. And then down here, the place where the line crosses the horizontal axis is the horizontal intercept point. But in this case, we're using the letter A to represent the age. So that would be the A-intercept point. And so if we have a nice grid like that, we can make a pretty good guess. So if you're wondering where did they get 71, 0, how did they know that was 71? Well, they're just guessing at this point. There's no arithmetic or math, there's no equation. They just drew it on nice graphing paper and they're guessing it's about a 71. Same thing with the 106 over here. So they're guessing that this guy is about 0, 106 and this guy here is about 71, 0. Okay? Alright, so now let's interpret these back into the word problem. What do they represent? So this was ages, and then this was percentage of people that text messaged multiple times per day in some given year. So this is saying that 71% people that are 71 years old, right? This is the A variable. This is the P variable. So 71-year-olds, 0 what? 0% of 71-year-olds text message multiple times per day. That's what this is saying. Does that seem reasonable?
Yeah. No.
I think we could all guess it's probably low. It's probably not a huge percentage. But 0, there's got to be one 71-year-old out there that text messages multiple times per day. So that seems a little unlikely. What about this one? What's this one saying? 0 what? 0-year-olds, right? Does that make sense?
Yes.
Can we have a 0-year-old?
A few months.
So if you are, you have your 1-year-old when you're 1 year and 2 months, you still call yourself a 1-year-old, right? Yeah, when you're 1 year and 3 months, you still, this is a 1-year-old. Okay. What if you're 9 months old? You're 0 years old, right? So between day 0 and day 364 of your first 364 days of your life, you were 0 years old. So that part is okay, but it doesn't make sense in the context of text messaging. This is saying that 106% of 0-year-olds were text messaging multiple times per day. That doesn't make sense at all. How do they have a data plan? For one thing. 106%, right? We can't have more than 100% in this context, right? You can't have more than all of it. All of them is as far as it can go. You can't have more than 100% of people in this context. So the fact that this is over 100 is a bad thing. And also, it doesn't make sense that newborns would be text messaging. So obviously, our model is giving us bad answers at the tips out there. When that happens, we say that the model has broken down. Okay, so a model breakdown. So when a model gives predictions that does not make sense, or an estimate that is not a good approximation, we say that the model we say model broken down, a model breakdown has occurred, or the model has broken. Okay, so a model breakdown. Intrapolation versus extrapolation is another important thing. So interpolation is when we use a part of the model whose t-coordinates are between coordinates of two data points. Extrapolation is when we use a part of the model whose t-coordinates are between t-coordinates of any data points. Are not between the t-coordinates of any data points. What does that mean? So if I use this red line to make a guess about something we don't know, right? We're using our model to approximate things. If I use my red line here to guess things that come in this region here, then I'm really using values that come between known data points. Right? This is a known data point right in there. It extends down there. This is a known data point right in there. So if I use my red line to work within this region here, then those are interpolation values. Okay? Now if I use my red line to make guesses about values that are this way or that way of the green region, then that's extrapolation. Okay? And so what we want to note is that interpolation values are more reliable because they're trapped between real known data points. So I'm a lot more confident when I'm making a guess that is in this region, right? Interpolation. When I'm making a guess involving, way out here, it's out by itself. There's no other real known value points near it. So it's more and more likely that it's gibberish. It's not guaranteed. Maybe it's good, but maybe it's not right. Maybe something has gone wrong and the model is no longer doing a good job of predicting a real world situation. Okay? So way out there is extrapolation. The ones that are trapped between known data points are interpolation. We trust interpolation a lot more than we do extrapolation. Right, so there's another graphic of it. So the zone right in there, this little zone in here is interpolation. A little bit more trustworthy when we make our estimations from there. And then out here, well, if we have nothing else to go by, then we make a guess using that. But we just recognize that we are using extrapolation, and there's less faith, less confidence in our results. Good. Questions? Okay. So when we recognize that we have a model that has broken, right? So when we recognize that our model was doing pretty good for a certain region of the domain, but then all of a sudden it was giving us weird answers there and weird answers there, what we can do is go back and search for more information. Right? I know that this was doing okay, but then over here some weird stuff happened. So maybe we go out and get more information. Same thing over there, some weird stuff that happened over there. So we go out and we adjust our model. Maybe we add some things, like for instance, maybe we say children 3 years old and younger never send messages. We know that's true. But maybe starting at 3 years old, some kids start text messaging multiple times per day, right? That's when it starts. That the youngest known example that we have is some kid, he's on YouTube and he's texting, okay, he's 3 years old. That's the earliest case we know of. All right. The percentage of cell phone users who send and receive messages levels off, flattens out at about 5% for users that are 80 years or older. And also, the age of the oldest cell phone users is 116. So if you were given these 3 additional pieces of information, then maybe you can readjust this model, right? The model is the line, the red line in this case. You can readjust it a little bit to better fit this word problem. And so, for instance, you might get something that looks like that. Right? So it's kind of that curvy thing. It begins at nothing, right? So there's no values. It's undefined at 0, 0. Right? No results there. Or it could be a flattened line. So we could have sort of some flat there, and then it takes off very quickly. Looks like right around age 10, is when kids start getting, you know, phones and start text messaging. Does that seem reasonable to you guys? I'm not around any kids, I have no idea. Is that when kids start text messaging? Around 10?
Earlier, yeah.
10 or earlier? Okay. Well, again, this is based on information from some year back, and it's probably a while back since we kind of reach only like 80%, and I would guess that by today it's probably higher than 80%. So in this year, whatever this year was, around 10 years old is when kids started to really text message. They skyrocket up to like 80%-ish, and then, you know, things sort of level off for the various age groups. Okay, so this might do a better job of approximating it. Also notice that toward the end, when we hit the 70, 71-year-olds, then it just kind of flattens out. And it goes all the way out to the end. And what's that end point? Why did we stop there in the graph?
116.
Because the oldest person we know, the text messages, is 116 years old, so we just stop it there. So it does a slightly better job of approximating our situation. Good, good, good. Okay, so, you know, it's a weird curvy line, but for now, we're only going to focus on straight lines. So notice that even though it's kind of like this weird curvy thing, it's still, a straight line still does a pretty good job of approximating for a segment of the graph, right? So for a portion of it, a line does a pretty good approximation. So that's what we're going to be focusing on.